Hey, it's Coach Powers here, ready to take you on a Lewis dot structure trip. So we are going to talk about Lewis dot structures today. This is another lecture for our covalent bonding series. We have got, this is our 6.2B lecture, where we're going to continue talking about covalent bonding. Lewis dot structures are going to help us to figure out how these elements are bonding together in the way that they're sharing their electrons. And so this, again, is covalent bonding where they share electrons. We want to put them up on the board, and we're going to show you why, or how, I should say, they're sharing their electrons. Now, this is something that was developed by a guy by the name of Gilbert Newton Lewis, and he was a prominent chemist in his day, wanted to be a part of the Manhattan Project to work on the nuclear bomb, did not get chosen to do so. And kind of an interesting story there if you go into his story about what might have happened to him right after he had lunch with a student of his that did get chosen to work on the Manhattan Project. I'll let you read into that story and see what you find out. You might like it. He's also the guy that's responsible for coming up with problem sets. Supposedly before this guy, we didn't have problem sets in our textbooks, at the end of our textbooks, so that we would have, extra questions to work on in our textbooks afterwards for our homework. So anyway, seems kind of crazy that he's the guy that came up with that, but I read that somewhere, so it could be true. All right, so let's talk about what we're going to learn today. Our objectives for today are to write electron dot structures or electron dot notations for elements, and then predict the ion the elements will form, to draw the Lewis structures for molecules and polyatomic ions. Now, Lewis structure and electron dot notation, basically the same thing, okay? Those are pretty much synonymous. Explain the difference between single, double, and triple bonds, and then represent and explain resonance structure. So you're successful today if you can write a Lewis structure if I give you a formula for a molecule or a polyatomic ion. You are successful today if you can identify where the single, double, and triple bonds would be, all right, and how many electrons are being shared in the Lewis structure. You are successful today if you can recognize a resonance structure and when a resonance structure would be required, okay? And just basically show you how that resonance structure works. You are successful today if I give you an element from the representative groups 1 to 2 and 13 to 18, and you can give me an electron dot notation and the ion that it forms. And we'll start out with that one actually right away. So here it is, electron dot notation. What kind of ions are formed in these particular situations? This is just something that allows us to keep track of our electrons. So for instance, I have a big X here that we start with, but you can see that sodium is an example of one of these, okay? And so we're just showing, let's see, if it's in the first column, that means that it's got one valence electron. And so we just write out the valence electron next to the element symbol, just like that, okay? This is really simple. This is the electron dot notation, keeping track of the valence electrons and where they would be. Now, as you go through and fill them out, there's a couple different ways to do it. You can see on this example, they start by putting them one on each side of the element as you go down here, and then down here, you're putting one electron on each side so that you have kind of like an even distribution. And again, there's a couple different ways of doing that, but the idea here is that you want to think about what would it be doing if it were filling up its s and p orbitals, okay? And so after you filled up one on each side, then you'd start doing two on each side, right? And so you can start filling in until you get all the way around. Now, sodium is only going to look like that, but by the time you get down to neon, that's the one that's going to have electrons filling up every single spot. Now, if I were comparing these little spots to our orbital diagrams, okay, if I have my S and then I have my 3 Ps, then I would fill, and this is the part that's kind of funky because we have what's called sp hybridization. And so if you remember from the last lecture, I showed you that there were two s orbitals that were kind of connected to each other, and I kind of, well, we had a dotted line drawn around them, and I said it was hybridization. Well, sp hybridization is basically when the s and the p sublevels are combined to make one big hybrid sublevel. Okay, so sometimes this is what happens. Instead of filling up 1, 2, and then starting to work across there, they actually kind of combine and hybridize. Now, this is a hybridization between one element and another element. Okay, this isn't just one single thing, but this is where you would basically say, okay, I've got one dot on each of the 4 sides. All right, so if we were talking about like this one here, where we got one dot there, one dot there, one dot there, one dot there. That's kind of the idea that we have here. And then we start going through and then filling in the other dots. Now, when we are actually doing representation of this, if I, for instance, we're going to do magnesium, I am not going to care whether you put your 2 dots there or you put your 2 dots up there, okay, or if you separate them out and you put them one on top, one on bottom. I prefer that these electrons, my first 2 electrons would be in pairs, just because that's typically what your S sublevel would do, right? So if I were doing the magnesium atom, then my S sublevel would just fill up and one down. And so for me, I like to represent the magnesium with my 2 dots together, paired together, okay? So if I'm doing something that has just the S sublevel, then it works and makes sense to put those 2 together. But there's reasoning to talk about, putting them and separating them out as well. All right, so that's how you do the electron dot notation. You basically just make sure that you put little dots around the 4 sides. The part in the middle, the X or the element symbol, that's the nucleus. And those electrons around the outside are those valence electrons. Remember, you can have 8 valence electrons. That's kind of what they're going for, right, to get that octet. All right. As long as you have the right number of electrons and you don't put any more than 2 on a particular side, for the most part, you're going to be okay. Okay. Don't put any more than 2 on a side, though, because that just doesn't make sense, right? Unless you've got one of the exceptions like phosphorus or sulfur. So here's a Lewis structure. This is what it would look like if I had carbon and then chlorines. You notice that around the chlorines, I've got all these extra electrons. And so there's a part of the chlorines that are sharing, and that's the part that they're sharing with carbon. Remember, every line represents 2 electrons. So that line right there represents 2 electrons or 2 dots. So I could be drawing that out, and I could have drawn it out in a different way. If I wanted to, I could have drawn it out where I had carbon in the middle, and I was just showing my electrons around carbon, and I could just do 2 dots, 2 dots, 2 dots. These 2 dots are the same thing as that line, okay? And of course, if I were doing the full electron dot notation, I'd want to make sure I had all of my external electrons on my chlorines as well. These are the bonds, okay? This is 4 bonds, and it's bonded to 4 different chlorines. Okay, does that make sense? So let's take this a little bit further. It shows how the valence electrons are arranged around the atoms in the molecule. And again, remember the symbol of the element represents the nucleus. The electrons are the valence electrons around the outside. Now we have 2 types of electrons we want to talk about, the lone pairs and the bonding pairs, okay? Now, if I were to just draw carbon by itself like we showed on the last one, carbon is one that does an sp hybridization. It's in group 14, right? And so it's got it's 4 valence electrons, and so it typically has 1 on each side, okay? And so carbon kind of looks like that. Now carbon has 4 unshared, okay? Well, no, it's got 4 lone electrons, or 4 lone or unpaired electrons, okay? It's got 4 unpaired electrons, but it's gonna then be able to pair, once it's bonded with something, with 4 different things. And so that's why it can bond with 4 different chlorines. Now, if I were looking at chlorine's symbol all by itself, I would have 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. It's in the 17th column, right? And so how many of them are unbonded or unpaired? There's only 1 unpaired electron, okay? And so basically, there is going to be a place right there where carbon's electron can interact, right? So we can have a carbon electron. Let's make our carbon electrons with X's, and we can have a carbon electron connected to a chlorine, and they share the 2 electrons between them. The circle electron is chlorine's, and the X electron is carbon, and so they have a shared pair of electrons. So the places where they are unpaired becomes the place where they are shared. Okay, so unpaired electrons can become shared electrons in this case. Now the lone pairs are the ones that are non-bonding. So in this case, carbon has 4. All of carbons end up becoming bonding pairs. But chlorine, chlorine doesn't have all of theirs bonded. 3 sets of electrons on chlorine are not bonded. So it's got 3 pairs that are lone pairs. Okay, so chlorine has 3 lone pairs. Carbon has 0 lone pairs. Carbon had all of its unpaired electrons become paired up, and so it's got 4 bonding pairs, or 4 shared pairs. Okay? All right, and so you can write them in as dashes. Yeah, electrons can be written as dashes as well, like I said before. All right, so how do we draw Lewis structures? Well, there's a little rule, a set of rules that we're going to follow anytime we draw Lewis structures. Okay, so first rule is you got to count up all the valence electrons. So whatever compound you're dealing with, look at the different elements, count up all the valence electrons for all those different elements. That's your first rule. Okay, so let's say we're doing methane. Okay, methane is CH4. So how many valence electrons does carbon have? 4. So we add 4 right up there, and then we could do 4E. And then how many valence electrons does hydrogen have? 1. But how many do I have? I have 4 of them. So 1 times 4, okay, 1 electron times 4 hydrogens gives me 4 electrons. I add those up, and I have 8 valence electrons. So step number 1, find the number of valence electrons you have. Add them up. I have 8 valence electrons for methane. Step number 2, arrange the symbols. Now, carbon is typically going to be in the center. Hydrogen is never in the center. Hydrogen can only bond with one thing. So never put hydrogen in the center. Don't put hydrogen in the center, okay? So carbon, in this case, is going to go right center, okay? Carbon goes in the center, and then it says you'll have 1 central atom typically, and you'll see that we definitely have examples where we can go with 2 central atoms or 3 or 4, depending. But we're going to start with the easier ones. So we have 1 central atom. It's typically the least electronegative atom that goes in the inside. Okay, in this case, we're definitely going to have carbon. Hydrogen can never go in the middle. Hydrogen can never go in the middle. It only forms bonds with one thing, so it can't be in the middle of anything. So the least electronegative atom is typically going to go in the middle. Carbon is typically one of those. Remainder of the atoms go around symmetrically the central atom. So now I'm going to put my hydrogens around my carbon symmetrically. This is how we do Lewis dot structures. Not hard, right? Remember, hydrogen is always at the end or terminal. Halogens are at the end, okay? Chlorine is never going to be in the middle. Fluorine's never going to be in the middle. Bromine's never going to be in the middle. Iodine's never going to be in the middle. Acetine's never going to be in the middle, okay? These are the halogens. They're never in the middle. Why? Because they can only form bonds with one thing. And, of course, I say never. There are actually some exceptions to that. Sorry. Chemistry is full of exceptions. All right, anyway, distributed dots. So now I want to figure out, I've got 8 valence electrons. I need to distribute them. The first thing I need to do, you got to be thinking about trying to satisfy the octet rule, right? And so I want to try to get the octet rule satisfied. So I want to try to get 8 electrons for each of my atoms. Now, for hydrogen and helium, that's not going to be the case, right? Now, helium doesn't really bond with anything. But I don't need to get 8 for hydrogen. 8 only needs 2. And so I'm happy to get 2 for hydrogen, but I need to be getting 8 for carbon. Okay? And again, I just have to use my valence electrons. So let's start distributing them. 1, 2, 3, 4, 5, 6, 7, 8. Oh, so that was cool. It says that I have to do something else if I can't get 8. I have to start looking at how I would form double and triple bonds. I'll show you an example of that coming up. But for right now, this is a pretty easy one. I have distributed my electrons, And I've got 8 around carbon. Carbon's happy. All my hydrogens are happy because they have 2, and that's all they want. So now I can go ahead and change those into bonds. Okay, I can change them into dashes. All right, so I don't have to, but let's just go ahead and change these guys into little lines. Boom, 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 boom. Okay, now that is the same thing. Do I need you to do that when you're doing Lewis dot structures? No, I don't need you to do that when you're doing Lewis dot structures. It says to add brackets if you're doing polyatomic ions. So if I had a polyatomic ion, like let's say it is, SO4 2 negative, so I have an S and I have all of these oxygens around the outside, and then I would put brackets around it, and I would put a 2 negative on the outside of that. And so if I were doing something like this, I would make sure to have a bracket with a charge on the outside, okay? And we'll talk about whether or not that's actually a correct Lewis dot structure here in a second, but that's just kind of an idea what I mean by brackets. Okay, we're not going to do that in Lewis structure yet. And then the last one, number 5, check. Make sure that your total valence electrons are correct, that everything's got octets and duets, and everything's all good. Now let's do this SO4 real quick. Let's go ahead and start with step number 5, check. Let's see if I did this one right. Let's see if it makes sense. Okay, so I'm going to kind of erase that real quick. And let's look at SO4, 2 negative. If I have a sulfur, I have 6 valence electrons. And I have an oxygen, I have 6 valence electrons. But I have how many of them? 4, right? Times 4, which means I should have a total of 24 valence electrons for my oxygens, which means I should have 6 and 24, so I'm at 30 now. But I have an ion, and if you have an ion and it says that there's a 2 negative charge, that means you have 2 more electrons than you normally would. So I have to add those 2 electrons together. So when I do my total number of electrons, I should have 32 electrons for this structure. Now let's see if that's what I have. I can just go around and count them. I can see that everybody's got 8, but did I need to do double bonds? Did I need to do triple bonds? Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'm good. I just checked my work. I had 32 total electrons. Every atom there has 8 electrons. They're all happy, and I've done my job. So that's the correct Lewis dot structure for the sulfate ion, SO4 2 minus. Okay, let's see another example. You guys are just going to see a few examples here because this is a little bit tricky. It's a little tough to learn this. This is nitrogen trifluoride. Okay, what would it look like if I were writing a Lewis structure for nitrogen trifluoride? If you think you've got this already, give it a shot. Pause it and practice, all right? See what you can come up with. First step, count the valence electrons. 5 for nitrogen. Fluorine's got 7 times 3 is 21, which means if I add them all up, I'm going to end up having a total of 26 valence electrons, right? 21 plus 5. And again, how do I know how many valence electrons? Well, I can just look at the column number. That's in column 15, it has 5. That's in column 17, it has 7. Here we're actually looking at the electron configuration and adding those up. That's fine too. Okay. Step 2, arrange the atom symbols. Now, which one is less electronegative? All right, nitrogen is less electronegative, so it should go in the middle. And remember, fluorine never goes in the middle, with some exceptions. And so I'm going to put N in the center. And so N goes in the center, and I've got to distribute my other ones around the outside, right? So I've got to distribute my fluorines around the outside. I don't have to redraw that because that's already been done. Look at it down here, okay? So fluorines growing on the outside. Step 3 and 4, distribute the dots and draw the bonds. So I have to get 26 electrons, so we start counting them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, okay? 22, 24, 26. Oh, look at that. If I've distributed them all, fluorine has got 8, right? Fluorine has 8, 2, 4, 6, 8. This fluorine has 8, this fluorine has 8, and look, nitrogen has 8 too. 2, 4, 6, 8. Remember, those electrons count for the fluorine and for the nitrogen. And so it does count to have the electrons being 8 around nitrogen as well as the 8 around the fluorines, okay? And so that's how you double check to make sure everybody's got an octet. And whew, here you go. All right, so again, we have 3 single bonds. We have 10 lone pairs. That's 26 total electrons. Yeah, and fluorine has 3 lone and 1 bonding pair. 8. Nitrogen has 1 lone and 3 bonding pairs. 8. Yep, everything's good. All right, so we did it. Did you get it right? Did you try it on your own? Did you get it right? Let's see what I can have on the next one. Now, this is a potential catalyst, but I want you to just go ahead and see if you can write out the Lewis structure for CH2O. Now, I'm kind of mean here by giving you something like this, right? Because you haven't seen one quite like this. But let's see if you can do it, all right? Pause it and practice and come back. All right, so now we are back. How many electrons for carbon? We have to have 4 electrons for carbon. We have 1 each from hydrogen, so that's 2 total. I have 6 from oxygen, so I should have a total of 12 valence electrons I need to distribute. Carbon is a central atom. Carbon goes in the middle. Hydrogens can go around the outside, and oxygen could go on the outside or in the middle, but because carbon's the least electronegative, it should go in the middle. First thing we just do is we put our bonding electrons in. So I've got 2, 4, 6 electrons. So what I like to do is I like to subtract my 6 electrons. How many more do I need to go? I've put 6 in. I need to add 6 more. Now, if I were to do this, I would be bad. Why? Because hydrogen only has 2 electrons, okay? So this is where you might have messed up or where it might have got confusing. Hydrogen can't have any more than 2. So the only ones hydrogen ever has will be the ones that are bonding when it's in a bonding pair. So I can have these 6. I could do 2, 4, 6. Uh-oh. Okay, now I'm done. I've just run out of my electrons. And again, I'm kind of mean because I gave you one of these and we didn't practice one quite like this. This is one where we're going to need to do that double, triple bond kind of thing. So what happens is if you get to a point and you've added up all and distributed all your electrons and yet somebody's not happy, carbon's not happy here, right? Because carbon only has 2, 4, 6. It doesn't have this 7th and 8th electron, so it doesn't have an octet. It's not happy. Oxygen's happy. Yes, it's got 8. Hydrogens are happy because they've got 2, but carbon is not happy. If you get to a point when you've distributed all your electrons and you've got one that's not happy, then you take from the rich and you give to the poor, okay? That's what you do. You're taking from oxygen and you're going to share in the space between oxygen and carbon. So I take 2 electrons there and I put them here. Okay, so take from the one that has enough and give it and put it in the space between the 2 where the one that didn't have enough is there and the one that had enough is there. So in this case now oxygen now has 8 because it's got 2, 4, 6, 8. Carbon has 8, 2, 4, 6, 8, and the hydrogens have 2, and so now you're happy. Did you get that one right? Impressive if you did. Good job if you did. Okay. That would be the Lewis structure for CH2O. And there's, I'm going to go ahead and put that stuff there. You guys can see what that looks like. Another way to draw it, does it matter if they're, if the oxygen's down here and the hydrogens are over there? No. In 3-dimensional space, that is exactly the same thing as what I just did, okay? So it doesn't matter where you put them because in 3-dimensional space, it's all the same. You can twist and rotate that molecule and you'll have the same thing either way. All right. Lewis structure for the carbonate ion. So I showed you briefly the sulfate ion, but let's go ahead and do the carbonate ion real quick as well. All right, so carbonate ion, again, I have 4 for my carbon, right? So we're going to go ahead and CO3 2 minus. Carbon has 4 valence electrons. Oxygen has 6 times 3 is 18 valence electrons. And then I have to add 2 more electrons, right? Because it's a 2 negative charge. And so I've got a total of 24 valence electrons that I have to put around this thing. Carbon goes in the middle, and then oxygens have got to go around the outside. That's step 2, right? Now, I need to put bonds between each thing that has bonds. There we go. I've now used up 6 electrons. I started with 24. I've just used 6. I have to distribute another 18. Let's start doing it. 2, 4, 6, 8, 10, 12, 14, 16, 18. Doesn't matter where I go. No, it doesn't. As long as you're going around the outsides of these that will have more than, can't do that to hydrogen, but as long as you do that to things that have, that want to have 8 electrons, I could have started up here, started counting around and went short on carbon. Or I could have started down here and go all the way around. It doesn't matter where you start that 2, 4, 6, 8 thing, but I've done my 18 electrons now. And look, I am deficient. This oxygen is not happy because it doesn't have all of its electrons. It's only got 6. So remember, the rule was to take from the rich and give to the poor, right? So in this case, which one's rich? Carbon has all it wants. I'm going to steal from carbon, and I'm going to swap one right there in between, okay? So now I got to check my work because it says that's what I was supposed to have. Let's see if I have a total of 24 electrons, and let's see if they're all 8. This one's got 8, this one's got 8, this one's got 8, this one's got 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Boom, I'm done. Except for my final step in doing polyatomic ions is that I have to put it in brackets and put the charge on the outside. Okay, so that's doing the electron dot structure for a polyatomic ion. That's how you would show that. Cool, huh? Lewis dot structures are fun. And so again, I'm just going to leave this up. I'm going to put this up, and then you can pause it if you want, and you can look at it in slow-mo. Uh-oh. Did I count wrong? What did I do wrong? Did I count wrong? Oh, my goodness. If I counted wrong, I'm a silly guy. I did 4 for carbon. 6 times 3 is 18. 18 and 22, 24. Okay, yeah, they're doing the double bond here. So they were 2, 4, 6, 8. If you went back a step here, that was just confusing the way that we have that there. If you look at this and they go through the check, they're saying, no, you have too many electrons. You have 26. You're not supposed to have 26. Okay, good. They're checking their work. They just showed a bad one. Sorry, I forgot about that. But they're showing a bad one. And so now they're checking, no, it's not 26. It was supposed to be 24. So something's wrong. When they went through and did it, they messed it up and they did it wrong. So somebody screwed that one up, and you'd say, that's too many electrons. If they're checking it, too many electrons, boo, bad. No, you can't do that. And so in this case, they're saying what we should have done instead is have a double bond here, and so that way they share. Okay, so my example was great. Where does the double bond go? Doesn't matter. Now this is something we're going to talk about now. It's called resonance structures. Again, in three-dimensional space, you're not really going to be able to tell the difference between these things. You're going to be flipping this thing around, and it's going to, pretty much look the same. But each of these oxygens is a different oxygen. So if you have different ways in which that double bond or that triple bond can be situated around the atom, then you have what's called a resonance structure. Okay, so this is a resonance structure, and it's because you can have the double bond on any one of those 3 different oxygens. And here's the thing, it actually exists at one point or another on all 3. Like, it doesn't just stay in one place, okay? These are electrons, and electrons are moving around all the time. And these are basically like hybrid orbitals, right? And so they're moving around and sharing between the different oxygens. And so we call this a resonance structure because it exists in any of those different states at any particular time, okay? Now, it will only be in one at a time. It can't be in multiples at the same time. But those are resonance structures. Those are structures where it can have more than one single Lewis structure representing it accurately. And so I could have used any one of those 3 and it would have been still true. And so that's what we call a resonance structure, okay? All right, so possible Lewis structures that have multiple representation are called resonance structures. And again, why do we write them? Well, typically because we have a double bond present and it can be drawn with more than one location, sometimes maybe a triple bond. The actual structure is an average or a hybrid, okay, resonance hybrid of what those three structures in this case were, okay? All right, your turn. Let's practice it. You've got to do the nitride ion, all right? Pause it and practice. Do it. Don't cheat and just fast forward through this. Pause it and practice it. Do it. And you're back after practicing it. Good job. All right, let's see how you did. NO2 negative. Nitrogen has got 5 electrons. Oxygen, there are 2 of those, times 6 electrons is 12. I have 1 negative charge, okay? So I have to add 1 electron. So I have a total, oh, this is weird. I have a total of 18 electrons, right? It's a good thing because 17 would have been tough to figure out how to distribute. And so I've got a total of 18 electrons. Look at this. You could have come up with 2 structures, either the double bond on that oxygen or the double bond on that oxygen. Now, notice what we use here. We use the double arrow to show that either of those structures is correct. This is what we do when we want to show a resonance structure. We put a double arrow on it, okay? So put a double arrow anytime you're doing a resonance structure. So if you did the structure right, good job. Hopefully you put it in brackets. If not, it would be wrong. Hopefully you put a charge on the outside. If not, it would be wrong. I'm assuming many of you got this part right. Maybe a couple of you figured out that it should have been a resonance structure and you actually did like a double arrow saying, hey, it could be either. If you did that, you are amazing, all right? All right, so resonance structures, double bond can be on either side, so we got to use that double arrow. Okay, now we do have some exceptions to the octet rule. So we want to talk about these briefly. We're almost done here. We've got boron. It's happy with 6. What can I say? It doesn't need as much as everybody else. So boron can be happy with 6. So if we give you boron, you got to remember, because you will get some borons, that boron is an exception and it doesn't want 8, it wants 6. I know, weird, right? All right, beryllium is happy with 4 in its outermost energy level, okay? So you have some electron deficient examples, but you also have some electron abundant examples where you exceed your octet. You have more than 8. Phosphorus is one of those. It likes 10. Sulfur likes 12, okay? Basically, anything in the 3rd period or heavier might end up having, some of these exceptions, right? Because they're using some of the empty d orbital slots, okay? And that's where you get some of these weird, things where you actually have like sulfur hexafluoride, and sulfur has 6 fluorines surrounding it. So sulfur has a total of 12 electrons. It's kind of weird. Here's sulfur hexafluoride. Here's phosphorus pentachloride, okay? Some weird examples, but you need to know that there are exceptions to the octet rule. And yeah, just be ready, right? Chemistry is full of exceptions. All right. So your final job here for the molecule HCl, determine the number of valence electrons, draw its Lewis structure. HCl, are you kidding me? That's not even a challenge. At this point, you can do that without even blinking, right? It's just an H, and it's got a double bond, and then it's got the chlorines around it on the outside. That's too easy, right? If you want to make that 2 electrons, fine. If you want to make it a little line, that's fine. All right, let's see if we can do what we set out to do. Our objectives, let's review them. Can we now write electron dot notation for the elements? Boom, I can give you an element. You can draw the electron dot notation. As long as you know its number of valence electrons, you can, right? Can you predict the ion an element will form? Well, yeah, because however many electrons it has, okay, 1 through 3, okay, if it has 1, 2, or 3 valence electrons, that's going to form an ion of a +1, a +2, or a +3. If it has the 6, 7, or 8 electrons, valence electrons, sorry, 5, 6, or 7 valence electrons, it's going to form a -3, a -2, or a -1 ion, okay? So the carbon is right in the middle. It could go +4, -4, the ones that have 4 electrons, right? But that's how you're going to know that. Draw the Lewis structures for molecules of polyatomic ions. Yeah, we can do that. Polyatomic ions, remember, have the brackets. Explain the difference between single, double, and triple bonds. Single bond has how many electrons shared? Double bond has how many electrons shared? Triple bond has how many electrons shared? 6. Okay, so we got 2 for a single bond, we've got 4 for a double bond, and we've got 6 for a triple bond, okay? And then, can we explain resonance structures? If it can have more than one way of drawing it, you have to draw each of the ways that can be drawn. It's a pain. All right, so your criteria for success. Are you successful? You will be successful if you can, and I bet you can. If I give you a formula for a molecule, like, how about arsenic trichloride? Yeah, you can draw its Lewis structure. You're like, what? Yes, you can. Try it. Give it a shot. I bet you can do it. You can identify single, double, and triple bonds in Lewis structures. Yep. 2 electrons, 4 electrons, 6 electrons. And you can tell me how many electrons are being shared there. You can recognize resonance structure. It has a double arrow, right? And you know why it's being represented, because it can have more than one way of being represented. And then you can use groups 1 and 2 and 13 through 18 and show me what the electron dot notation is and predict the ion that it will form. You got this. It's easy. It's fun. If you have questions, please make sure that you are asking me. I need to help you when you have questions, and I love to help you when you have questions. Please ask me questions. I live to answer your questions. Yes, I do. All right, you have a very good day, my friends, and I will see you later. Hey, be kind to each other, and God bless.